So good day to everyone. So in the last video, we have derived the Bernoulli's theorem equation, the Bernoulli's equation, and so in this video, we are going to uh, give the explanation for this Bernoulli's theorem, and we are going to prove this theorem. Okay. So the Bernoulli's the equation is, as we already know, that P divided by rho plus half V squared plus GH, which is equal to a constant value. That means the total energy of the incompressible non-viscous fluid flowing from one point to another point without any friction remains constant through the motion. This total energy means is the pressure energy as well as the kinetic energy as well as the potential energy. So all the total energy will be equal to the constant value. So according to this theorem, this suppose the height of an element for fluid of density rho above the ground level is taken as a h, and suppose if it is moving with the velocity of v and the pressure is actually taken as a p, then the total energy of the volume is given by this equation. So I can write this equation in terms of E, which is equal to p plus rho v squared divided by 2 plus rho into gh. Suppose this rho is the liquid, the density of the liquid which we have considered, so that I can just multiply this equation by rho, so then we will get this equation, which is equal to E. So this E is a constant. E is a constant value. So if suppose if you consider the 2 points in this fluid, suppose you consider a tube, and if you consider 2 different points, and you are going to measuring the velocity, height, and pressure in the 2 different points. Let us take the velocities as which can be written as v1 and v2 in the 2 different points of the tube, and the height, this is equal to h1 and h2. Similarly, the pressure at 2 different points is taken as p1 and p2. So if this is the case, then I can write this is actually constant, so that I can equate these 2 quantities. That means I can take this as p1 plus rho times of g into h1 plus rho into v1 squared divided by 2. This is the total energy of the one point, which is equal to the total energy of the another point which we have considered. That is can be written as p2 plus rho times of g into h2 plus rho into v1 squared divided by 2. So this is the stable equilibrium position. That means the total energy of the Bernoulli's equation for the one point and the another point. Suppose this kinetic energy per unit weight is actually called as the velocity head. That means this rho times of v1 squared divided by 2 is actually known as the kinetic energy part. So that is actually known as the velocity head. That is the v squared divided by 2 is actually known as the velocity head. And this the potential energy per unit weight is called as the gravitational head, which is equal to the height h, so that I can write this the part h is equal to the gravitational head. That is actually h into g. Similarly, the pressure energy per unit weight is actually called as a pressure head, which is equal to this p divided by rho, which is actually known as the pressure head. Therefore, if we combine all these 3 values, so v squared divided by 2 plus hg plus p divided by rho, which is equal to a constant value, that is the Bernoulli's equation. Or I can just multiply this equation by g, so that as I divide this equation by g, then I can get rho square v squared divided by 2g plus h plus p divided by rho into g, which is equal to a constant value. So here this v squared by 2g is the velocity head, h is the gravitational head, and the rho by p divided by rho into g is the pressure head. So the total energy will be equal to the constant value. Suppose in case of a liquid flowing along the horizontal pipe, suppose if you consider pipe is which is actually in a place in the horizontal position, and the liquid is actually flowing in the horizontal pipe, then this gravitational the gravitational head is actually equal to constant value, so that I can write this v squared divided by 2g plus p divided by rho into g, which is equal to constant. Suppose if the liquid is actually traveling in the horizontal pipe. Or I slightly modify this equation, just dividing this equation by rho g, then I will get p plus rho into v squared divided by 2, which is equal to a constant value. So this is here, this p is the static pressure, and this p rho v squared by 2 is the dynamic pressure. So which is equal to a constant value. So this equation is this expression is actually shows that the greater velocity corresponds to the decrease in the pressure, as well as the vice versa, or that is the points of maximum pressure correspond to those of minimum velocity. And this principle, this expression is actually used to determine the speed of the fluid by means of this pressure. Okay. So if we know the pressure of this the liquid which is actually passing through the any tube, then we can easily manipulate the speed or velocity of this fluid using the pressure. Okay, so in order to prove this theorem, what we are going to consider is I am going to consider a tube. So the pipe as shown in this figure, which is actually having the two different cross sections, or it doesn't have the uniform cross section. So suppose if you assume that the fluid is actually moving in this tube with a streamline motion along this non-uniform tube. So this A and B are the two different points where we are going to measure the velocity as well as pressure, and both the A and B are actually having the different heights from the horizontal plane, which is taken as a H1 and H2, and the A1 and A2 are the area of cross sections of these two places A and B. So the velocity of the liquid at this the point A is taken as v1, and the v2 is the velocity at the outlet with the point B. So according to the equation of continuity, we know that the velocity at this point is actually lesser than the velocity at this point B, since the area of cross section at the point A is actually greater than the area of cross section at the point B. And also the pressure at the point P A is actually taken as P1, and the pressure at point P2. So according to so we assume that this A1 is actually greater than A2. Therefore, the velocity at this point V2, which is actually greater than V1. Therefore, the fluid is actually going from here to here, from one point A to B, it actually accelerating because the V2 is greater than V1. Therefore, suppose the work done per second on the liquid entering at this A is taken as W1, that is the work done, where you have to move the fluid from this point A, that is actually given as the force at A multiplied by the distance moved by the liquid for unit time. The distance moved by the liquid per unit time. So that I can write it as force is equal to P1 into A1, and the velocity is taken as V1. Therefore, the W1, which is equal to P1 A1 into V1, that is the work done. Similarly, we can calculate the work done at this point B, that may be taken as the W2. So W2, which is equal to the work done per second on the liquid leaving at the U tube B, the tube B. So the W2, which is equal to P2 A2 into V2, where the P2 is the pressure at the point B, A2 is the area of cross section, and similarly the V2 is the velocity of the liquid. So suppose if you consider the net work done, so the net work done by the fluid to passing from the point A to B, which can be given as W, which is equal to the W1 minus W2. Okay, so you can just take the subtraction of this values of W1 W2, we get so the P1 A1 V1 minus P2, A2 and V2. But we already know that from the equation of continuity, the A1 V1 which is equal to A2 V2. So that if you apply this equation of continuity in this equation, I can write this as the A2 V2 is equal to A1 V1. So that I can just take this A1 V1 as common minus into multiply by the P1 minus P2. So that is the total work done by the liquid by passing from point A to point B. So this work done is actually used to change the potential as well as the kinetic energy. So that suppose if you do this work, then the potential energy will decrease and the kinetic energy will be increased. So that the decrease in potential energy can be written as the decrease in the potential energy, which can be given as, so we know that the potential energy is equal to mgh. So the m can be written as the A1 V1 into rho into g into height is actually the height difference between the h1 minus h2. That is the difference between the height between the point A and B. So this is the decrease in potential energy. Similarly, if the potential energy is decreased, then the kinetic energy will automatically increase. So that increase in the kinetic energy can be written as half mv squared. So that half m is actually A1 V1 rho and v is actually the velocity difference. So V2 squared minus V1 squared. So this is the increase in kinetic energy. Therefore, the total energy, the total gain in the energy can be given by just subtracting the kinetic energy and potential energy. Will get the total gain in the energy of the system when the liquid is actually flowing from point A to point B. So that I can write the total gain, which is equal to half into A1 V1 rho into V2 squared minus V1 squared minus this potential energy, the A1 V1 rho into G into H1 minus H2, which is actually equal to this potential the work done. So that I can just substitute this as a work done, that is A1 V1 into P1 minus P2. That is actually equal to this difference in kinetic energy and potential energy. Or I can just expand this equation. So A1 V1 into P1 minus A1 V1 P2, which is equal to half into A1 V1 rho into V2 squared minus half into V1 rho into V2 V1 squared minus A1 V1 rho into G into H1 plus A1 V1 rho G into H2. So in all this coefficient, the A1 V1 is actually common in all the parts, so that I can just divide this equation by A1 divided by A1 V1, so that I will get the P1 minus P2, which is equal to half into rho into V2 squared. Similarly, minus G into H. So that I can just rearrange this equation by point one, but the point of A and B, so that I can write this as P1 plus half into rho V1 squared plus rho into G into H1, which is equal to P2 plus half rho into V2 squared plus rho into G into H2. Or I can write it as P1 plus half, so P plus half rho into V squared plus rho into GH, which is equal to a constant value. And you can further simplify this equation by just dividing this whole equation by rho G. I get P divided by rho into G plus half of V squared divided by G plus H, which is equal to constant. Okay. So this is nothing but the Bernoulli's equation. Here you can see this P divided by rho G is nothing but the pressure head plus the half V squared by G is the velocity head plus the H is actually the gravitational head. all this the sum of all this is equal to a constant value. And so the Bernoulli theorem can be stated as when an incompressible non-viscous fluid flows in streamline motion, the sum of the pressure head, velocity head, and gravitational field remains a constant throughout its motion. So that is the Bernoulli theorem, and this Bernoulli theorem is actually used to solve many different problems, many fluid mechanics problems. And we are going to see some of the example problems where we are going to use this Bernoulli's equation and Bernoulli theorem to solve the problems. Okay, so the first problem is the water flows through a horizontal tube of varying cross section at a place the velocity is 0.3 meters per second when the pressure is actually 0.016 meters, 0.016 meter of the mercury. Find the pressure when the velocity is 0.6 meter per second. So we are assuming that there are two different points A and B, and these 2 points are actually in the horizontal level. So the potential energy of these points are actually same because there is no height difference. Therefore, the P1, P2 of the P1, P2 can be the pressures at the points A and B, and V1, V2 may be the velocities at two different points A and B. Then according to the Bernoulli theorem, I can write it as P1 plus half into rho V1 squared, which is actually equal to the P2 plus half into rho V2 squared. So here we know that this P1, which is equal to given by this 0.016 of meter of Hg, so which can be converted into the Newton per meter squared. For that, I am going to multiply this value by 13,600 into 9.8 per Newton per meter squared, so that I can convert this meter per Hg2 into the Newton per meter squared standard SI unit. So the velocities of the two points is given as V1, which is equal to 0.3 meters per second, and V2, which is equal to 0.6 meters per second. Therefore, we have to find out what is the pressure of the another point. Okay, so we already know this equation, so that I can write this equation in terms of P2. So that means P2 which is equal to P1 plus half into rho into V1 squared minus V2 squared. So I can directly substitute all the values. So the P1 is actually given as 0.016 into 13,600 into 9.8 plus half into the rho is actually for the water, the density is actually 1000 Newton per meter square. So the 1000 into the velocity, that means 0.3 whole square minus 0.6 the whole square. So which can be just calculating the value, the final value of the P2 will be equal to the 1997 Newton per meter squared. So this is the pressure at the point P2. Suppose if you want to convert again from the pressure from Newton meter square to the meter of Hg mercury, then I can again just taking the values 1997 divided by 13,600 into 9.8, which will be equal to the 0.015 of meter of Hg. This means mercury. Okay, so this is the pressure at the point B is 0.015 meter per meter of Hg. Okay, so the second problem is, so the water flows along the horizontal tube of which the cross section is not a constant value. So you have to calculate the change in pressure when the velocity of flow is changes from 0.1 meters per second to 0.2 meters per second. So since in this problem too, this water is actually flowing in the horizontal direction, that means there is no change in pressure. Sorry, the potential energy is not changes because both points are in different same height. So that again I can write this Bernoulli's equation as P1 plus rho into V1 squared divided by 2 again. This is equal to P2 plus rho into V2 squared divided by 2. So I can just take the so I can take this P2 in the left hand side and this quantity in the right hand side. I can just take the difference P1 minus P2, that is equal to the rho divided by 2 times of V1 squared minus V2 squared. So the velocity changes is actually already given from 0.1 to 0.2 meters per second, so that I can easily calculate the pressure difference. That is equal to the rho is again it's a 1000 because it's a water divided by 2 and 0.1 squared minus 0.2 squared. So the final answer will be minus 15 times of Newton per meter squared. That is the pressure difference P1 minus P2. So here this negative sign indicates that due to the increase in the velocity, the pressure is actually decreasing. Okay, so you can see this pressure is at V1 is actually 0.1 and the pressure at point P2 is actually 0.2. There is a change in the increase in velocity. Therefore, there is a decrease in pressure. Okay. So you can also work with a couple of problems. So the third problem is, so a railway locomotive lowers that a tube in a reservoir of water in between the rails. So the immersed tube is horizontal and the upper end is actually 3 meters above the surface of water in the reservoir. If the locomotive is actually running at 48 kilometers per hour, you have to calculate the speed at which the water rushes out of the upper end. Okay, so this is the problem. So here we can assume that the lower end having the height of h meter below this water surface. Therefore, the total energy of the upper end of the tube is which is equal to the total energy of the lower end of the tube. So according to the Bernoulli's principle, I can write the equation of half V2 squared plus P2 divided by rho plus H2 into G, which is equal to half into V1 squared plus rho P1 divided by rho plus H1 into G. So in this quantities, we know some of the quantities, that is the V1, which is equal to 48 kilometers per hour, so which can be written in terms of meters, so that I can write it as 13.33 meters per second, and P1, which is equal to the P0 plus H times of rho into G, because the atmospheric pressure we have to take it into calculation, and similarly the P2, which is also equal to the P0. That is, the tube is actually out of the water, so we have only take the atmospheric pressure as a calculation for the P2, and H1, which is equal to 0, that is the reference point, and H2 can be written as H plus 3 meters, so that I can write this as H plus 3, and we have to find out what is the V2. Okay, therefore I substitute all these values into this equation, and I can write the equation as half V2 squared plus P0 divided by rho plus H plus 3 times of G, which is equal to half into the other values which V1 and everything we know, so that we half into 13.33 meters per second the whole squared plus P0 plus H into rho G divided by rho plus the height which we have taken H1 is 0, so that we can check the 0, and then we can find out this. Finally, we can find out the V2 squared, which is equal to 13.33 squared minus 2 times of 3 into 9.8. Before going into that, I further simplify this equation like the half V2 squared plus P0 divided by rho plus Hg plus 3g, which is equal to half into 13.33 the whole square plus this one I can write as P0 divided by rho plus H times of G. So here you can see this is P0 divided by rho, and this P0 divided by rho will get cancelled. Similarly here Hg and Hg will get cancelled. So the remaining terms are, and similarly this half and half will also get cancelled, so that the V2 squared, which is equal to 13.33 the whole squared minus 2 times of this 3g, because if I multiply this and multiply this by 2, you will get 2 times of 3g, so that you can just substitute the values now. 13.33 minus 2 into 3 into 9.8, which will give you the value of 118.9, or I can convert this into the meters per second, that is almost equal to 10.9 meters per second. So that is the V2 square, the V2 value. The V2 squared is equal to 118.9, so the V2 will be equal to 10.9 meters per second. Okay, so I can also solve one more problem using the same Bernoulli's equation. The fourth problem is, so a fire engine pumps water from a hydrant at the rate of 1000 liters per second. It ejects it from the nozzle 5 meters above the surface of water with a velocity of 10 meters per second. They have to calculate two things. One is the the pressure difference between the water and the pump and the nozzle, as well as the power of the engine. So again, we can use the Bernoulli's theorem for Bernoulli's equation for this. We have two different points. For two different points, we have to write the total energy of the system. So that for the point P1 at the point A, we can write P1 plus half into rho V1 squared plus rho into G into H1. In the second point, we have a P2 plus half into rho V2 squared plus rho into G into H2. So since we have to find out the pressure difference between the pressure and the pump and the nozzle, we can take the pressure difference of these equations, which will give you the P1 minus P2, that is equal to half into rho V2 squared minus V1 squared plus rho into G H2 minus H1. So here we can easily substitute the values. So half into rho is actually 1000, since it's the water, and that difference of means the V2 is already given, V1 is 0 because that is the starting point of the nozzle. So I can write it as 10 squared minus 0 squared plus again the rho is again 1000 into G is actually 9.8 into the height difference is actually taken as a 5 meters plus 5 meters. So I can take it as 5. So I can just directly find out the value. The value will be 9.9 into 10 power 4 Newton per meter squared. So that is the pressure difference between the point P1 and the point A and B. Similarly, we can find out the power. So the equation for the power is actually the pressure difference into the flow rate, the rate of flow. So the rate of flow is again given as 1000 liters per second. So that I can write this as P1 minus P2 we have calculated as 9.9 into 10 power 4 multiplied by the rate of rate of flow, that is I can write as a cubic meter. So that I can write as 1 because it's 1000 liters per second. So that I can write as 1 meter cube per second. So I can just write this 1 meter cube as 1, which is equal to 9.9 into 10 power 4 watts. So this is the power of the engine. So similarly, using the Bernoulli theorem, we can solve the different problems. Okay. So I stop here, and the remaining how to apply this Bernoulli theorem and to derive the Torseli's theorem and the Venturi meter, which I will take it in the next class. Okay. Thank you.